Okay, dear children, now we'll study about elastic strain energy in tension. Now, in the earlier discussion of a bar and simple tension, we have seen that during elongation under a gradually increasing load, that is, if you have a bar, it is subjected to a load which is gradually increasing, work was done on the bar, and that this work is transformed either partially or completely into potential energy of strain, and this potential energy will be stored as strain energy. So if the strain remains within elastic limit, the work done will be completely transformed into potential energy and can be recovered during a gradual unloading of the strained bar. So if completely recovers its original shape, then the whole work done in elongation is stored as potential energy and the whole will be released during the unloading of the bar. If the final magnitude of load is P and the corresponding elongation is delta 1. So if P is the final load and delta is the final elongation, we can show the tensile stress strain diagram like this, or the load deformation curve as OA. Now, in which the y-axis, the values on the y-axis represents the load and values on the x-axis represents the deformation. So here, let P1 be an intermediate value of the load. Let P1 be the intermediate value of the load, and delta 1 is the corresponding elongation. So, during a gradual increase in load, let P1 be the intermediate value of load and delta 1 be the corresponding elongation. Now, a small increase in the load delta P1 causes a small increment in elongation, that is d delta 1. So, the work done by P1 during this elongation is P1 into delta 1, that is load into deformation. It is represented by the figure as this shaded portion. So, if we are taking the increment as very small, we can take the area, we are providing a small allowance in the increase of P1 during the elongation. The work done will be represented by the area of this trapezoid, that is A, B, C, D. Okay. So, in the total process, that is from the increment of load from 0 to P and the total elongation 0 to delta, you can take the total work done as the area, the total work done in the process of loading when the load is increasing from 0 to P is the summation of many such elemental areas, and is given by the area of triangle OAB. Okay, so this represents the total energy stored in the bar, and we can represent it as capital U. Okay, area of triangle represents the total energy stored, and it is represented by the letter capital U. And this is known as strain energy. So area of triangle represents the total energy stored in the bar. So what is the area of triangle? This triangle OAB has an altitude of P. This value is P. And base equal to delta. So what is the area of triangle? Area of triangle is half into base into altitude, that is P into delta by 2. Strain energy capital U equal to P into delta by 2. Now we can substitute here. Instead of delta, you'll get another form of this strain energy. P by 2 into delta is PL by AE, where L is the length of the bar, A is the area of cross section, and E is the Young's modulus of elasticity. So you will get another form of equation, strain energy equal to P square L by 2 AE. Now if you are substituting, this P is equal to A into sigma, and then sigma is equal to small e into capital E, and E is equal to delta by L. You will get another form of the equation, strain energy U is equal to AE into delta square by 2L. Okay, so you have got different forms of strain energy. U is equal to P into delta by 2, where P is the total load and delta is the total elongation, or U is equal to P square L by 2 AE, where L is the length, A is the area of cross section, and AE is the Young's modulus of elasticity, or you'll get the equation U equal to AE into delta square by 2L. So we have got the equation for strain energy in tension as U equal to P square L by 2 AE. Now the strain energy per unit volume is called resilience. That is, U divided by A into L is equal to P square L by 2 AE into 1 by AL, which is equal to P square by A square into 2E. Okay, or you can write this is equal to sigma square by 2E, or you can write this is equal to 1 by 2 into E square. Since we know that sigma is equal to P by A and E is equal to delta by L. Okay, so you have got the equation. Strain energy per unit volume is resilience. It is equal to sigma square by 2E. Now we can write from this, you will get another equation for strain energy. Strain energy per unit volume, you know, it is 2 sigma square by 2E. Therefore, strain energy into volume is equal to, this is equal to sigma square by 2E into volume is A into L. L is the length and A is the area of cross section. So this becomes half into sigma by E into sigma into A into L. So this is equal to half into strain into stress into volume. So another equation for strain energy is half into stress into strain into volume. Okay, now you must know about a term known as modulus of resilience. Modulus of resilience is the greatest amount of strain energy per unit volume which can be stored in a body without permanent set. So what is the strain energy per unit volume? It is sigma square by 2E. This is one form. And modulus of resilience is the maximum amount of strain energy per unit volume which can be stored in a body without permanent set. Now you must know about another term, proof resilience. Proof resilience is the maximum strain energy which can be stored by a body without undergoing permanent deformation is called proof resilience. And how can we obtain it? It is obtained by substituting stress is equal to elastic limit. Now you have studied about the stress strain curve for steel, isn't it? So you have a portion known as proportionality limit where stress is proportional to strain, and the second limit is known as elastic limit, that is it will regain its original shape, but stress is not proportional to strain. That point is known as elastic limit. So it will not regain its original shape. It will regain its original shape on removal of this load, but the variation will not be straight line. So that the stress corresponding to that point is known as elastic limit. So in the stress strain curve you have two limits. Proportionality limit, the stress corresponding to the point where stress is proportional to strain and the variation is a straight line, and on removal of the load this material will regain its original shape, is known as proportionality limit. And the next point is the stress corresponding to the point where when you remove the load the material will regain its original shape, but from this point to this, from the proportionality limit to the elastic limit, this stress will be not proportional to strain and the variation will not be a straight line, it will be slightly curved, and that point is known as elastic limit. So if in this equation for strain energy we are substituting the stress corresponding to the elastic limit stress, then it is known as proof resilience. Okay, so these terms are important. What is resilience? Resilience is the strain energy per unit volume. What is modulus of resilience? The greatest amount of strain energy per unit volume which can be stored in without permanent set is known as the modulus of resilience. And proof resilience is the maximum strain energy which can be stored by a body without undergoing permanent deformation, and it can be obtained by substituting stress equal to the elastic limit. Okay, so this is what you have to study about strain energy in tension. Okay, so in the case of shear also you can find out what is the elastic strain energy. You consider a small element subjected to shear force F. It is in pure shear. The lower side AD of the element is taken as fixed, and only the work done during the strain by the force P at the upper side is considered. Okay, so here also shear stress is proportional to shear strain, and you can form an equation: work done is equal to shear force into deflection by 2, that is F into delta by 2. Now you know that delta is equal to PL by A. In the same form you can write in the case of shear strain as delta is equal to FL by A into G. Okay, so you will get an equation for delta as FL by A into G. Now you know what is shear strain energy, F into delta by 2. Substitute FL by AG instead of delta. So you'll get strain energy equal to F square L by A 2 AG. Or you can rewrite it as U is equal to AG into delta square by 2G. So what is the strain energy per unit volume? By substituting Q equal to F by A and phi equal to delta by L, you can write strain energy per unit volume as Q square by 2G or phi square G by 2. Okay, so we can write this strain energy for shear also in another form. Strain energy for shear is half into shearing stress into shearing strain into volume. So you will get half into Q into phi into V, or instead of substituting Q by G instead of phi, you will get strain energy equal to Q square by 2G into volume. Okay, so you must remember this equation: strain energy for shear is equal to half into shear stress into shear strain into volume. Thank you.